first video for section 4.2 in AP Calculus on the mean value theorem for derivatives. We're also going to talk about some other things pertaining to graphs of derivatives related to what we've already been discussing with maximum and minimum values. But first, we're going to talk about the mean value theorem for derivatives. So I'm going to state it and I'm going to kind of illustrate for you exactly what it's talking about. So the mean value theorem for derivatives says that if you have a function that is continuous at every single point in a closed interval, so this is only going to apply to a closed interval where they say from 0 to 4 or something like that. So if the function is continuous in that entire closed interval and it is differentiable at every point within that interval, then what the mean value theorem tells us is that there is at least one point somewhere between A and B, so point B would be an x value, at which f prime of c equals f of b minus f of a over b minus a. So f prime of c, this is the derivative at c. And then f of b minus f of a over b minus a, this is the slope between points A and B. So that's good old 6th grade slope. So what they're saying is that if we connect point A and point B together and find the slope of that secant line, what the mean value theorem tells us is that there has to be some point between point A and point B where the tangent line would be parallel to that secant line. So scroll down a little bit. For example, I'll just illustrate it. I'll put down here some space. All right, so let's say that I have point A here, and point B here, and then my graph looks something like this. So notice that the graph that I drew, it is continuous from A to B. There's no jumps or vertical asymptotes or anything else like that, or fold. And it's differentiable from A to B because I don't see any corners or cusps or vertical tangent lines or discontinuity. So because those two conditions are true, I know that if I was to find the slope of the tangent line from point A to point B, then there has got to be at least one point somewhere between A and B where if I draw the tangent line at that point, it's going to be parallel to that secant line. So I'm going to try to eyeball the best I can. So maybe here, for example, it's my point forward. There we go. That tangent line would be parallel to my secant line, so this could be a p-value of about equals 1, because I'm thinking maybe right about here also, roughly, would be another C value. There's not necessarily going to be more than one, but there's got to be at least one somewhere between A and B where the tangent line is parallel to the secant line and therefore has the same slope. The important thing, though, is that you verify that those conditions are met before you can apply the mean value theorem. So the conditions are is that the graph has to be continuous from point A to point B, and then that it has to be differentiable from point A to point B. If either one of those are not met conditions, then we can't even apply the mean value theorem. So you would say mean value theorem does not apply, and you would explain why, because there's a discontinuity somewhere, or it's not differentiable somewhere, or something like that. So let's look at an example of an application. Oh, nope, we're going to jump to Rolle's theorem. Excuse me. So a special case to the mean value theorem is Rolle's theorem. And it says that if y equals f of x is continuous at every point of the closed interval from A to B, and differentiable at every point of its interior. So notice so far those are the exact same conditions as the mean value theorem. But it has a third condition as well. F of A is equal to f of B. What that means is that point A and point B have the same y value. Then what we then would know, based on Rolle's theorem, is that there has to be at least one point C between A and B where f prime of c, the derivative, is equal to 0. So let me illustrate that one for you. So let's say that I have point A here, and so point B should be over here somewhere, and they're at the same y value. I have no idea what my graph may look like from point A to point B, other than the fact that it has to be continuous and it has to be differentiable in order for Rolle's theorem to apply. and the fact that A and B have the same y value. So since they have the same y value, I mean, essentially this is the mean value theorem. It's just special. If I was straight up going to apply the mean value theorem to this, I would connect point A to point B, but what would that slope be? It's going to be a slope of 0 because that's a horizontal secant line. So Rolle's theorem just kind of, I mean, it is the mean value theorem. But think about what we know about situations where a derivative is equal to 0. A derivative is going to equal 0 at any maximum or minimum values on a continuous graph. So this right here could be one p-value, this right here could be a p-value, this right here could be a p-value. So I mean, it's a special case in the sense that you would know that there has to be a maximum and or a minimum point somewhere between point A and point B, because there has to be a place where we would have a horizontal tangent line where our derivative would equal 0. But essentially, as long as you understand the mean value theorem, you can apply Rolle's theorem as well, because it works the exact same way. So now we're going to look at an example where we could possibly apply the mean value theorem. So this example wants us to show that the function satisfies the hypotheses, so we'll talk through that, of the mean value theorem on the given interval from A to B. And then we're going to find the value of C in the interval from A to B that satisfies that equation, and this should be an equal sign right here. That's all. All right, so we have the function f of x equals x squared plus 2x minus 1 on the closed interval from 0 to 1. So I know that x squared plus 2x minus 1 is a parabola. Parabolas are always continuous because they don't have any holes or vertical asymptotes or jumps. So that's the first condition of the mean value theorem. It is continuous. I also know that it's going to be differentiable on any interval that I choose because it has no corners or cusps or vertical tangent lines or discontinuities. So that's condition number 2. So as far as part A goes, you could just say f of x is both continuous and differentiable on the closed interval from 0 to 1. So then, since the hypotheses are met, part B is where we actually apply it. So we're going to find where this p-value would be that has a tangent line that would be parallel to our secant line from point A to point B. So the interval, this is A and this is B. So the first thing that I would need to do is I need to actually find f of B minus f of A over B minus A. So if you want to, you could just individually find f of b, so it would be f of 1, by substituting 1 into the original function. So we get 1 plus 2 minus 1, so that's 2. And then we can substitute 0 into the function. So we get 0 plus 0 minus 1, which is negative 1. So f of b minus f of a over b minus a, that's going to be 2 minus negative 1 over 1 minus 0. So the slope from point A to point B is 3. Now what we're looking for is where does f prime of c equal 3? So we would need to know what f prime is in order to answer that question. So we would take the derivative of our function. You get 2x plus 2. And what we're looking for is if we substitute c into that derivative, when would it equal f of b minus f of a over b minus a? So in this case, when would 2c plus 2 equal 3? At that point, I mean, the only calculus involved there was on finding the derivative. Now we're just simply solving an algebra equation. We subtract the 2, divide by the other 2, and so when c is equal to 1/2, then at that point, its slope at that specific point would match the secant slope from x equals 0 to x equals 1. If they wanted to, so this c value is an x coordinate of 1/2. So then if they asked you what the y coordinate was there so that you could get an actual coordinate pair, then you could just take the 1/2 and substitute it into your f of x function. But notice they didn't do that on this particular problem. I'm just saying in general, if they ever asked you for that, that's how you would go about it. All right, so that covers mean value theorem. The next thing that I want to talk about, this kind of takes us back to what we've been talking about with extreme values. And really, this shouldn't be anything new for you because we basically talked about it when we were talking about finding maximums and minimums. Finding where a function is increasing and where a function is decreasing. That all goes back to the sine lines or the wiggle graphs that we made with that first derivative function. If the first derivative is positive in an interval, then your function is increasing in that interval. If the first derivative is negative in an interval, then your function is decreasing. So this would be f prime is positive, would mean the function is increasing. F prime is negative, would mean the function is decreasing. And I know it's all written out there for you, but to me it seems a whole lot easier just to say f prime positive, f is increasing. F prime negative, f is decreasing. So there you go. And that goes to the corollary down there below. That basically just sums it up exactly what I said in that corollary right there too, so I'm not going to bother to read through that. But you have it there all spelled out nice and neat for you. So for example, if I have a function f of x equals 2x cubed minus 12x, and I want to know where it's increasing and decreasing, this is something that you did back in accelerated geometry or in Algebra 2, where you would have to find the maxes or mins, and then you said, okay, my graph going up or down, and your answers would be basically the entire domain of the graph. You have to write it in the intervals, and most people kind of really struggled with that in accelerated geometry. But now is our opportunity to do really well at it. You're actually going to do this the exact same way that we find maximums and minimums. So you start by finding the derivative of the function. So this one would be 6x squared minus 12. Then you're going to look for where it equals 0 or does not exist. In this particular case, this x squared graph is going to exist everywhere. So that's not an issue. So we're just going to solve for when it is equal to 0. Do my algebra there. So I get x equals plus or minus square root of 2. So remember, those numbers are now the things that we put on our sine line for our derivative graph. And so now I'm going to choose a number in each interval of that sine line to substitute into my derivative. So over here to the left, negative square root of 2. I don't even know off the top of my head exactly what that value is, but I know that it's less than 2. So as far as this first interval over here on the left goes, as long as I choose any number less than negative 2, or really negative 2 or less, then I'm going to be fine. So I could even choose negative 2 in here. So when I substitute that, it's my derivative, and just like with maxes or mins, I don't really care what the number is, I just care is it a positive or a negative. So negative 2 squared is 4 times 6 is 24. 24 minus 12 is going to give me a positive answer. In my second section, I would use probably 0. We have 6 times 0 squared minus 12, which is going to give you a negative number. And then in my third section, I'm going to use positive 2. But again, you don't have to choose the same numbers as long as you choose the number in that interval. And we would get a positive answer. So at this point, what we have done in the past is we'd be looking for our maxes and mins. But if I'm just looking for intervals of increase and decrease, I basically just read my sine line from left to right. The first section of my sine line starts at negative infinity, and it stops at negative square root of 2. That section is positive, so that's where my original graph would be increasing. Then the next section of my sine line goes from negative square root of 2 to positive square root of 2. That section is negative. So my original graph would be decreasing from negative square root of 2 to positive square root of 2. And then lastly, that third section starts at positive square root of 2 and it ends at infinity. And I marked it with a positive sign. So that would go back up here on the increasing interval. So that's the intervals of increase or decrease. Now, you could also now state for me where the maxes and mins occur. If we've got a graph that's going up, down, and then up, I know that I would have a max value when x is negative square root of 2. And for the sake of time, I'm not going to go through and find that y coordinate. And then I would have a minimum value when x is positive square root of 2. So if they asked you for those, it's all the exact same work. Now you can just answer 4 different things instead of 2 different things. So that wraps up the first part of section 4.2 for us.